Good afternoon. It's lovely to see so many people here. I'm David Parks. I'm the Dean of the John Paulson School of Engineering and Applied Sciences. And we're a mission-focused school on building a bridge between technology and society. And we're focused on finding solutions to some of the biggest problems in the world. And we see climate, sustainability, and energy as one of the most important intellectual pillars of the Paulson School. And to that end, we're investing heavily in new faculty and research, exploring new educational programs, and supporting a long tradition of high-impact, cutting-edge research. And for a long time, we've had leading work together with the FAS on modeling, measuring, and forecasting as it relates to climate and climate change. And this has always involved doing path-breaking science and has often involved developing clever new technology as well. And today, we're increasingly turning to science and technology for solutions to the climate crisis. And I'm delighted to bring together a group of esteemed faculty from the Paulson School, also along with an interdisciplinary scholar who works across schools, to share some of this high-impact, cutting-edge research as part of this very important Harvard Climate Action Week. So this is a panel about innovative climate technologies. And I think it's especially good today that our moderator is Frank Keutsch, the Stonington Professor of Engineering and Atmospheric Science, the current area chair within the School for Environmental Science and Engineering, and soon taking a new leadership role as the SEA's Academic Dean for Research. So that's my bit done. Frank, over to you.
Thank you very much, David. Yeah, so today we're going to talk a little bit about, and you'll hear from some people in the broader SEAS community about this sort of degree of technological innovation to address the climate problem. And sort of take one step back, and I'll talk a little bit, and then I'll introduce, and you'll hear from all from the panel. So one of the fundamental problem we have with the climate challenge is sort of the high temperature, which really is a result of the accumulated energy in the climate system. And, my microphone was not.
All right. That better? Back row, can you hear me? All right. So the fundamental climate problem is that you have all this built-up energy in the climate system that's stored in the climate system. That elevates the temperatures. And what we need to do is prevent more buildup of energy in the climate system, which means that we really need to cut greenhouse gas emissions to zero so that we sort of don't have additional greenhouse gases that result in more accumulation of energy. And the climate system hasn't even reached equilibrium yet. The other thing I think and that is critical, and that requires technological solutions. So the idea where we're going to talk about today is really the idea of what technological solutions are being pursued and how much I think can happen in that arena. So that means we need technologies that generate energy, obviously, without emitting greenhouse gases. So that's one important role for technology. The other parts you can imagine, which we will only touch on today, is the second part is you could also say if we actually want to try and restore climate to some degree, we have to have a way of getting more energy out to space and to get that energy and climate system back down and temperatures go down. Because if you just cut the greenhouse gas emissions to zero, that energy that has been stored in the Earth system is there for a long time, and it takes a long time for that to go back down. If we want to get rid of more energy space, there's really only two ways you can do that. You can either reduce greenhouse gases, really actively taking CO2 out of the atmosphere, perhaps methane, because that will allow more infrared radiation to go out to space, and that will cool the planet, right? Because you're removing some of the insulation. The other part we won't talk about today is that you could reduce the amount of sunlight that is reaching space by changing the reflectivity of the planet. That was a topic of a panel yesterday. And those are really the things we have to do. And for all those things, whether it's removing greenhouse gases from the atmosphere or going into a new energy technology, that all requires new technologies that we're going to hear some about. Now, one thing I want to say is that quite often when we hear about climate, the discussion quickly turns quite grim and glum. And I actually want this panel to show more that I actually think there's some reason for optimism. It's a very tough problem. It's a big, a big challenge for us, but that there is reason for optimism. And just as an example, one of the reasons we can see is that the technological advances, for example, the price of PV probably came down faster than most people predicted initially. So there are examples where we can see that some of these technologies really can become impactful quite quickly. All right, so science and technology, and kind of why science and technology at Harvard is in a special place. One of the things is that the science and engineering at Harvard, we're not a very large unit, and that actually has a lot of advantages because it makes it quite nimble. It makes it possible to collaborate with other people. It also makes possible, there's a lot going on in the moment at the translation space of actually taking these new technologies and doing translation that go into sort of startups and companies. There's also a different kind of translation that is not specifically the right word. But one of the things that's also special about Harvard is that we have all these other schools. We have policy, we have the law school, we have the business school. And because Harvard isn't that large a unit, I think those connections can also translate what is known about technologies that are emerging into the policy space and informing policymakers, I think, faster than it is perhaps possible at other places. So I think those are really important connections here. Now, if you look at some of the panel over here, I specifically, sorry, Lena, I looked past you. I'll know in a second why. That one of the reasons why, another reason that gives me optimism is actually when I look at the university, at the students and at young researchers, there's an incredible degree of passion, creativity, and smart people around that really want to solve the problem, right? And that's partly why I sort of thought we should, in part, have a very young panel, because when I look around, these young people are really what give me optimism, because they have the problem, of course, that they kind of have to solve the problem, because it's more their problem than my problem or Lena's problem, because they're younger. But I actually also, if you hear what they will be talking about, I also am quite optimistic that they actually will help solve the problem and not just have to. And I think academia, again, I talked a little bit about Harvard, academia really plays a special role as well, because we do have the research and education, and having those two combined in one unit in a place like Harvard, where these young, incredibly bright, passionate students that come in as undergrads really already get exposed in perhaps even their first year to cutting-edge research and have the ability to work in a research lab, do undergrad research, learn what's going on at an early age, is really a special opportunity. And this combination of the research that is happening in Cs, for example, that goes into translation of the companies, can have a large real-world impact. But I would also argue that actually the impact we as faculty, even though, of course, we may all think that we are the most important and glorious people in the world and our research is super important, I would argue in most cases the impact we have on the world is actually much bigger through all the students, the vast number of students that we have in classes that we meet with. And so this merging of education and teaching, I think, is another thing that gives me some optimism. And so with that, I actually sort of want to stop, as I've sort of rambled long enough, but sort of give you an idea that it's really this combination of having science and engineering embedded in a broader context and in small units where there's a lot of collaborations, which I hope you'll hear more about. And what we'll do now is I'll pass on to Lene Hau, who's in applied physics. She's a professor in applied physics. I'll introduce also Zach Schiffer, who is a fairly new tenure-track professor in Cs, who are incredibly excited about his work, was really bringing new energy and ideas. And lastly, we have Danielle Tisch, who is a postdoctoral fellow in a really interesting collaboration between Cs and the Graduate School of Design. And it's one of those examples that is meant to highlight how these collaborations can happen in a place like Harvard that result in unexpected new ideas. Lena, you take it.
Yeah, well, thank you, Frank. I'm apparently the old one on the panel here. But I mean, so obviously we have this grand existential problem, the climate problem. And we in SEAS felt that we should and could do more. And in particular, in the last couple of years, we have really been working on, really expanding what we are doing both in science, engineering, and in education. And the interesting thing is, and I'm sure all of you guys know, this is a really multifaceted problem. And so it really requires collaboration between people in different fields. And it's also a problem where some of the facets, some of the problems are so difficult that you can't do it with engineering alone. You actually need to develop new science to develop or to solve the problem. And that's where, in many ways, SEAS is unique, because we have this amazing connection between the applied sciences and engineering. And we can kind of start in the lab of a scientist, and this scientist might discover something new and fantastic. Then we get the engineers in play, and it might be, once you start looking at, is this actually a practical thing you guys have discovered? It might be, it's not. So this sort of back and forth between the scientists and engineers is really, really important, because the devil is in the details at every step of this process of trying to develop something that we see in the lab, all the way through engineering, making a practical prototype, and then taking it, scaling it up to an industrial scale up. And so the connection between the applied sciences and engineering, and then also the fact that we are situated in the Boston ecosystem, where, Boston is actually becoming the leading place in the US for green tech. So we can kind of take what we develop at SEAS, and then, with incubators, startups, and sort of make use of this whole ecosystem. And in SEAS, and we sort of, both David and Frank talked about that, we have sort of a broad array of scientists in SEAS, and it goes all the way from our colleagues in environment and Frank and his colleagues in environmental engineering, science and engineering. And these guys they understand the atmosphere, and what they don't understand, they try to learn. They understand the atmosphere, the oceans, climate more generally, and also trying to figure out what are the drivers of climate change. And then they develop novel observational methods, both local field measurements, but also remote observations, airborne remote sensors. And then try to make sense of all these observations. And then, it's really a big data situation where they want to couple it with AI, machine learning AI, and try to be able to predict climate on the local scale, which right now, with current computational methods, is not really possible. And that way you can really start to get into quantitative risk assessments. And then once these guys tell us we have a problem, then we in other parts of SEAS can really get started and get into gear. And that's where some of, for example, Zach gets into play, and Dan as well. For example, what can we do? We have a problem, and how can we decarbonize our energy system? And that requires, for example, our ability to do energy storage, because as we know, renewable energy from solar and wind is intermittent, so we have to have ways to store that. So battery research is one way of doing it, and we certainly have colleagues in SEAS doing very serious work in that space. Carbon capture, that Frank was also mentioning briefly, capture the CO2 and then try to convert it. For example, with electrochemistry, convert it to useful products to actually have negative CO2 emissions. and conversion of our chemical industry and industrial processes, because that's actually an enormously, there are enormous carbon emissions from the chemical industry, and that's precisely the kind of thing that Zach is working on. Our colleagues in electrical engineering, they look at power electronics, for example. High power battery charging, you really need to deal with electronics in different ways. And also power electronics if you want to drive electric airplanes. And then we have others who are analyzing the whole energy system and the electric grid structure. And then our friends in computer science, if you think about AI, generative AI in particular, is enormously energy hungry. And right now, the energy being used corresponds to the energy that we use for the aviation industry. And the hunger for energy in AI is exploding. So that's where we really need to be thinking about more efficient hardware and more efficient algorithms. And all of these fields that I'm talking about here is just to give you a sense of what we are doing in SEAS. All of this is represented in SEAS, either currently by current faculty or what we will be doing, hopefully very shortly. Because as I sort of mentioned a couple of years ago, we really started this process of really taking a look at what do we need to do, which faculty do we have, where do we have gaps. So we actually ended up, and this is actually quite unique, I would say, for Harvard, we actually were able to run a cluster search where we will end up with 5 to 6 new people. Zach Schiffer, again, to just keep pointing to Zach for now, was actually our first hire as part of that cluster process. Zach started in just this past January. And then hopefully, in very short order, this has been a long process, area, really SEAS-wide. It hasn't been confined to individual isolated areas. So this has been a very well, really good process to kind of get all of SEAS involved. And hopefully in short order, we'll be able to hire more exciting people to actually cover all these areas. As I mentioned, it's really a multi-pronged problem. And the fact that SEAS has a very, very open, porous structure is really important because we can really use the synergy between these different areas, and we really need to be working together. And let me mention that the students, our wonderful students, are actually pushing us really hard because they are super excited about this. They really want to work in this field. And so our plan is to come off this collaboration we have had on this cluster hiring process to actually create a new educational program, a holistic program that will be both broad and deep. We have a groundswell of student interest and sort of very typical response I'll meet if I talk to a student and sort of mention what we are trying to do. It's like, oh my God, I'm a sophomore. How fast can you get this program running? Will it be in time for me to be able to do this? So there's really a lot of excitement about that. And then finally, let me mention again that SEAS is just wonderfully situated within Harvard. We have, connections to the humanities, the Kennedy School, the Business School, Law School, Medical School, School for Public Health. And whereas SEAS is the one doing the scientific, engineering, and technical solutions, this problem we are facing, the climate problem, requires close collaboration with people in economics, people who do policy, like in the Kennedy School, cultural considerations, ethics. So that's where these connections that we can create within Harvard are extremely important. And I'm really looking forward to more collaborations between SEAS and the Salata to really implement these SEAS-wide initiatives, reaching into Harvard, a wide Harvard program. Thank you.
Thank you, Lene. Zach, why don't you tell us a little bit, as we just heard, Zach is a very new assistant professor with us. Why don't you tell us about sort of one project, why you chose that project, sort of what's the challenge there, and what's sort of the real world impact you believe this will have sort of in a larger climate arena could be?
Yeah, great, thank you, yeah. So I guess as you guys have heard, I just started January 1st, so I'm pretty new here. Assistant professor in School of Engineering. And the area I work on is decarbonization of the chemical industry. So basically this means in some sense, about 30% of the sort of US CO2 emissions come from industry. And there are some big ticket items like iron and steel we heard about sort of the beginning of yesterday, and cement. But there's also this whole breadth of various chemicals that are being produced from petrochemicals, things like plastics, adhesives, fertilizer, agrochemicals, pharmaceuticals. All of these produce a significant amount of CO2, and we need to decarbonize these as a sort of our route to net zero. What makes this interesting and sort of a very difficult problem is the fact that the fossil fuels here are not just the fuel for these processes, right? We don't just burn them to heat them up or to drive these processes. The fossil fuels are actually the feedstocks. So the carbon that you see, in our plastic, the carbon that's in the pharmaceuticals, the various chemicals that we work with, this carbon comes from fossil fuels like natural gas or petroleum or like that. And so not only do we have to decarbonize the actual energy, we have to decarbonize the chemistry itself. And so we are, though, you talked about optimism, we're kind of at a sort of unique point in time right now where not only do we have these sort of cheaper electricity and renewables from like PV, we also have access to renewable carbon and renewable feedstocks, things like CO2 that we're capturing and like biomass. And so we sort of can combine this renewable electricity with the renewable feedstocks to start, in some sense, supplementing and rebuilding the chemical industry to be more sustainable and to avoid some of these CO2 emissions as we build up. So I, in particular, work on electrochemistry. This was mentioned a little bit. It comes up. It's the idea here that, in some sense, think of a lithium-ion battery or a fuel cell, but instead of using electrons to store and convert energy, we're directly dumping these electrons into a chemical bond to sort of make a new bond or to break a bond. And so I'm focusing on, how can we make plastic, or how can we break down plastic? How can we make fertilizers more efficiently? How can we make sort of specialty chemicals and pharmaceuticals? So as a sort of specific example, something that we sort of just thinking about and just looking at this would be like nylon. Nylon 6, it's all over the place. We use it throughout. The interesting thing about nylon that I actually learned sort of in the past few months is that for every kilogram of nylon we produce, the process also produces over a kilogram of waste chemicals on the side. So that's like, that's a lot of waste chemicals. Not only are we wasting energy sort of making these products that are kind of useless, but then you also waste more energy in terms of, disposing of these chemicals. So, we're looking at the nylon process and saying, how can we make this more efficient? How can we reduce its waste? How can we come up with alternatives that don't require, for example, high pressures of hydrogen gas or high temperatures? And how can we come up with new ways to separate it out that avoid some of these wastes? And so then, and that'll sort of decrease the energy or increase the energy efficiency, decrease the greenhouse gas emissions significantly. And it's generally applicable beyond just nylon, right? Nylon's sort of a nice case study, but similar processes are used to make things like detergents or other chemicals, other polymers along the way. So yeah, that's sort of the 3-minute summary there of what we're working on.
Thanks, Zach. Daniel, why don't you sort of give us the same perspective on the project you're working on?
Yeah, absolutely. So yeah, thank you, Frank, and thank you, Cease, for the ability to be here and sort of share some of our work. As I mentioned, I am a postdoc here at Cease, but I'm a little bit of the oddball as I'm an architect by training and I teach over in the Graduate School of Design. And I'm here really to represent a collaboration between Cease and the GSD, between the lab of Jennifer Lewis here in Cease and the MAPS group led by Martin Beckholt over in the GSD. And really our work is focused on the development of carbon negative building materials. So the ability to sort of take carbon dioxide out of the atmosphere and store it in the built environment itself. As architects, we know that buildings and the built environment play an outsized role in the climate crisis. About 11% of global carbon emissions are directly the cause of the extraction, manufacturing, and transportation of building materials. But simultaneously, we also know that we need to build more. With trends towards urbanization and population increase, there are some estimates that say we might need to actually double the floor area of the built environment by 2050. So we have a sort of double bind here. And so by developing materials that have a negative upfront carbon footprint, what we're really trying to do is take the enormous mass of the built environment and use that as a carbon storage device, allowing us to have functional products and allowing us to serve this need that we need to build more, house more people, while also finding a place to sort of put carbon dioxide in a sort of medium-term format for the life of the building and kind of get it out of the atmosphere. So often, as Zach mentioned, biomass, we're often looking at biomass. We're looking at using materials that come from photosynthetic organisms, but understanding it with a sort of full life cycle approach. Understanding that maybe corn to produce something like PLA isn't the answer because of all the energy that it takes to produce the nitrogen fertilizers and to sort of grow that corn. So instead, what we've been focused on recently is developing a new 3D printable structural material that's made from microalgae. And I know microalgae has a sort of bad rap out there. We often think of it in terms of algal blooms or these sort of dead zones that appear in our waterways. But we can actually reverse that cycle. And we can use the growth of microalgae to actually treat wastewaters. So we can take the excess nitrogen that's in our municipal wastewater systems, maybe agricultural runoff or other industrial effluents, and we can grow algae on those effluents, and we can then clean the water. We can sequester a lot of carbon dioxide in the process, and we have a lot of biomass that then we can work with. So we are working with biomass that comes from one of these nutrient recovery systems, and we are developing 3D printable materials from that. Algae, you might be surprised to know, has actually a high cellulose content. So it has a lot of structural potential to it, and it's actually an ideal size for additive manufacturing, particularly the direct ink writing method that's popular in the Lewis lab. So that small particle size actually drives the shear thinning effect that's required for that additive manufacturing method. So by combining the algae with water and a small amount of bio-based binders, we're able to make a 3D printable material out of it. We can optimize the rheology of that ink by tuning the particle interactions. And at the end of the day, we get a material that's about as strong as plywood, which is surprising when we consider the sort of microscopic cells that were our starting point. But I can tell you as an architect, the architecture community has lots of uses for things like plywood. There's a lot of things, a lot of applications that sort of material would be suitable for. So through like life cycle assessment, we've been able to prove that the material is actually carbon negative, that the carbon dioxide that was sequestered by the algae during photosynthesis outweighs the amount of energy that it takes for us to actually manufacture the material, thus enabling that carbon storage that I've been talking about. And while that carbon would be re-released to the environment at the end of the useful life, if the algae were to decompose or to burn, we've actually found that we can recycle this material as well. We can keep it in the loop by grinding it up and sort of reusing it over and over again. So this is really the sort of the aspiration that we're going for, pulling carbon dioxide out of the atmosphere and using it to produce functional products and to maybe build our homes and our schools in the future and keeping that carbon out of the atmosphere.
Thank you, Daniel. So one question I have for both of you, and whoever can jump in first. If you think about what you're trying to do, it goes all the way from quite fundamental research. And one thing I want to ask you about in that part, what was the hardest scientific or engineering problem to solve to get to the right product? But then it comes to for it to actually have an impact in the real world, it's a whole other set of problems. So, for example, Daniel, I don't know whether if you think about customers, do you think convincing a large branch in industry to go for a new product is always a tall order, right? It's like why we have to go for something new. There's a lot of investment in various forms that comes with that. So perhaps you can talk to both. What was the hardest problem on the science engineering side, and how you solved that, and how you think about, which as it hasn't happened yet, how do you think about actually getting that out in the real world? And then perhaps Zach can talk to that afterwards as well.
Yeah, absolutely. Thank you for the question. I think it's actually an interesting point, because one of the hardest aspects of the problem is actually the starting point, identifying what it is, the proper feedstock that could suit these technological needs. Really what we're looking at is an opportunity where we're asking the question of how does climate change and how these issues of the embodied footprint of our products, how does that intersect with developing technologies like additive manufacturing? What's really the right sweet spot between those questions? So there was a lot of work in even just identifying microalgae, in particular this nutrient recovery system, as the starting point for the research. But then I think on the back end, we face this problem where if you try to replace products in a one-to-one manner, you'll often lose out to the incumbent. So we look to add values and add functionalities in a lot of different ways in order to move the needle and convince the market that this is an appropriate solution. So when we think about technologies like additive manufacturing, it gives us the opportunity to shape our products in new and complex ways. We've created a brick material that essentially has a closed cell structure to it to trap heat and provide an insulative property to reduce the amount of insulation that might be needed in the building. So that's somewhere where we are trying to leapfrog the existing technologies by going beyond what is possible with the incumbent products. And I think that's really where our opening towards new markets lie.
Zach, what do you think?
Yeah, thank you. It's a great question. I think from a fundamental science side, a lot of it does, in similar mirroring Daniel here, is coming up with the problem definition in some sense, is looking at exactly, we say this process is, like for instance, fertilizer or something like that, right? Making ammonia produces a lot of CO2, it consumes a lot of energy. Where can we innovate here? But then if you look one level deeper, you realize that current methods to produce ammonia are actually pretty efficient. That innovating on that method, in a place like the United States is maybe a non-starter, right? It's already 50-60% energy efficient. And so identifying the exact niche and where you can start with a problem is quite important. And similarly, then when you want to transition things from the lab and scale up, I think in the chemical industry, which is a lot of what I think about, figuring out, moving things from creating a little bit of your desired product in a mixture of many other things to something that, chemical industry actually wants is the big step there. And sometimes it's like a separation and purification problem. Is that yes, I can produce something really valuable, but, if the industry is already set up to deal with their own feedstocks and their own processes, then they're not necessarily going to want to invest the capital cost to set everything up for a new process. And so getting that scale up and being able to integrate that into what already exists, I think is the big hurdle.
All right, so we have a third, what I will call younger person join us now, which is nice, Gage Hills, and he, so what we're talking about, Gage, is examples of a specific project that you're working on, that goes from a scientific engineering aspect and how you think about how do you actually get that into the real world, what actual impact can it have. And so perhaps you can tell us about one of the projects that you've been working on. You can also use that mic, whatever it is.
Okay, yeah. Thanks so much, Frank. It's an honor to be here. I'm sorry you had to say my name because I'm incredibly embarrassed to be so late to this. I had this on my calendar that it was tomorrow, and I was just sitting at home writing paper. But it's, yeah, no, I really feel terrible. But yeah, one of the areas that I'm super excited about this, and like sort of Frank mentioned, this bridging like a technical impact, or like the sort of technical innovations and how this can connect to like climate impact in the real world. So my background is in energy efficient computing. So I'm a circuit designer. My research group works on making energy efficient integrated circuits. So using different types of semiconductors to compute very quickly while using as little energy consumption as possible. So we often think of using energy as our sort of valuable resource in order to compute stuff quickly. Things like computing like a training model for ChatGPT or something like that. I think what I'm really excited about is it feels like there's this kind of global push or transition from thinking about like energy consumption as our kind of valuable resource for doing computing, like computing quickly, to thinking of that valuable resource as like the carbon footprint of computing. And this sort of comes into play in two areas for computing. There's kind of there is a sort of nice parallel between energy consumption and carbon footprint for chips that are sort of like out in the field and like running computations. Because in order to get that energy consumption, you often have to burn some kind of natural resource, which then has some carbon footprint associated with it also. But one of the areas that is sort of less traditionally thought of by circuit designers is the carbon footprint associated with like physically manufacturing computer chips. And what's really interesting is that for a lot of systems these days, if you do some of the analysis, you can see that the energy consumption and the carbon footprint associated with like physically manufacturing a computer chip, like think about all the sort of silicon layers and different types of metals that you have to put on that wafer, all the energy it takes to do the depositions, the different types of like gases that you have to flow in order to get the materials to be there, like where you want them to be. Like that whole process of manufacturing the chip can have a larger carbon footprint than the chip has like during its entire lifetime of operation over like many years. And so what this is really exciting is there's a team of researchers in electrical engineering and computer science at Harvard that we've gotten some seed funding from Salada, which has been awesome. Also getting recent funding from the National Science Foundation for putting together a sort of like an ecosystem for how computer chip designers should like think about this problem of trading off like carbon footprint for computing performance. All the way from the beginning of the life cycle, like from when the chip is like being manufactured in the commercial foundry to the end of its life when it's like being recycled or whatever. And it's really exciting because there's a lot of like sort of technical challenges associated with this. Like, okay, well, how do designers actually like how do we actually make these trade-offs, right? Like, can you use sort of less resources? Like, how much are you willing to sort of trade off? Like, okay, maybe I'm okay with having like a sort of 10x lower carbon footprint if I sort of compute twice as slow. Like maybe that's a trade-off I'm willing to make. But maybe I'm not willing to sort of, use 2x lower carbon footprint to run 10 times as slow, right? So how do you actually do this from a technical side? And then there's also the sort of like more challenging from my point of view as an engineer, like how do you get actually like companies to provide designers with like the models that they need in order to actually compute the carbon footprint of the systems that we're designing, right? Like when we design our circuits now, like we have like ridiculously accurate models for like how much power all the transistors are going to use down to sort of like the picoamp in every picosecond, right? We literally can like simulate all this stuff. But when it comes to carbon footprint, it's just like, we're just not there yet. We just get these like gross numbers like, okay, company X's carbon footprint is, this much like over this year. And so how do you actually like connect that down into the design parameters that that a circuit designer is going to use? So yeah, that's a summary of it. It's great. Super exciting. I know I took up some time, but yeah, it's great to be here again. And thank you, Frank and Lena, Zach, everyone for organizing this.
Thank you, Gage. Before we'll open up for questions to the audience in a second, I'll ask a question that's perhaps a little unfair. And that is, in the solutions that generally are sought when we look at sort of solutions we're trying to find in the climate space, the focus is sort of really on, for very good reasons, sort of the energy consumption that we used to sort of in the Western world, what we're using, what we're doing, that's where the real focus is. If you think about where most of the growth in energy consumption will be happening, that's actually probably not here, right? That's in other places of the world. And one of the questions is, if one thinks about, you have a certain intellect times time that you're going to be able to invest. In the end, is that actually invested more efficiently in looking at the problems that we have where there's not as much energy growth, or actually looking whether perhaps in other parts of the world, they may need different solutions, which actually having newer solutions for them soon could have a potentially much bigger impact long term, not short term. So there's sort of a time scale question, but it's also hard to know what their actual needs are and engaging with those. And so one of the things I want to ask you, which is a little unfair, is do you think that these solutions that you're working on are really for a specific market, sort of close to home? And that's entirely okay. I'm not saying that's wrong. And how do you think about, have you thought about that? It could be in other parts of the world, this could be different. I just want to give one example. When we think about the grid, and we want to, how can we get energy savings in the grid and how that applies, a really important problem in the US and Europe. For example, if you look at Namibia, which wants to get really big in solar, wind, and making hydrogen, for example, they have the internal problem that a large part of the country is not actually electrified. So if they do that, they also have to electrify the country. But it's so sparsely populated that the kind of grid that we have in Europe or the US probably doesn't make any sense. So you need some other solution. So that, just as one specific example, and it's one that may not apply directly, but have you guys sort of thought about other parts in the world, or how would you go about thinking about spending some of your time on their problems and what they may need? So just, I don't know who wants to go first.
Yeah.
Do you want to go for it? Okay, I'll jump in quickly. I mean, I think I have two thoughts. In particular, when we're talking about energy, I spend a lot of time thinking about embodied carbon footprints, but we're also looking at developing new insulation products, right? Heating and cooling our buildings takes a lot of energy, and so we're looking at ways to use biochar as our sort of negative feedstock to be able to reduce the loads that are placed on the electrical grid itself, which is, I think, important in any context because it either means you're reducing sort of carbon emissions now or you're reducing the load on a sort of clean energy grid of the future. But the other thing that I'll tie into is this sort of idea of systems design when it comes to some of our sort of cultivation schemes. Given that we are sort of reliant on essentially waste streams, the one source of water that we know is going to increase in prevalence is wastewater. So if we are sort of growing our sort of products out of these waste streams, we could actually be providing clean water at the same time that we are providing sort of material products at the same time. So I think that's one of the aspects where we think there's a lot of potential moving forward to address the sort of needs of other parts of the world.
Thanks.
Yeah, I think it's a great question. It's something that I think we think a lot about in chemical manufacturing because there's always trade-offs in terms of scale, like distributed versus centralized production of chemicals. Right? I used the example of fertilizer earlier. If I were making ammonia fertilizer in the United States, I think we have like roughly one ammonia plant per every 2 states or something like that. That works out because we have great transportation, trains and roads and everything to ship it around to farms everywhere. It doesn't necessarily work out outside the United States, where the resources, the electricity is maybe distributed or not. The CO2 in the air is also a distributed resource potentially, and so there's a very different way of thinking, whether you're addressing problems sort of here in the United States or outside somewhere else. And I think a lot of the sort of small scale lab research does necessarily lend itself more towards a distributed chemical manufacturing drive. And so there is perhaps some synergy there, something that we definitely think about a lot.
Yeah, I mean, this is definitely something that we think about a lot in the semiconductor manufacturing, just because chip design is already a sort of global effort. I mean, no single company nowadays like manufactures like your entire computing system like from the ground up, right? Like we might have, you know, like TSMC in Taiwan is sort of like leader in most advanced like technology nodes. So they might do the actual manufacturing of all the transistors and metal layers, but they need to get their silicon wafers from maybe somebody else. And then you might get the chips from them and then send it to like a packaging house that's gonna sort of dice up the wafer like into little pieces to put on the circuit board. Somebody else might make the circuit board. And eventually then that comes to you and you run the system and use whatever sort of power consumption on your local grid. But yeah, it's like, it reminds me of this question we've been grappling with of like the carbon accounting. Like how do you sort of, I think there's sort of like two challenges. One is how do you sort of like optimize the overall carbon footprint like of everybody together? Like considering the fact that, you know, like TSMC might be working on their own kind of like local power grid for their like huge manufacturing facilities. You know, there might be different sort of renewable sources that are being used at like different stages of the system design. But then how do you also, so it's, yeah, I mean, one point of view, like if you were sort of like the like eye in the sky designer, like how do you optimize the whole thing? But then maybe even more challenging from like a practical point of view is how do you like incentivize like every single like player in the computing system manufacturing to like do what's like sort of globally optimal, given that they have their own, you know, things that they need to worry about. Like, is it really fair for somebody to like one part of that manufacturing chain to like take the bulk of the sort of carbon footprint while maybe their like supplier is, you know, being able to claim that they're sort of like carbon neutral or carbon negative. So these are sort of like, it's tough as like this combination of the technical challenge and the sort of practical challenge.
Mm-hmm.
Thanks. So before we go to questions of the audience, Lena, any sort of thoughts you want to add from a larger programmatic perspective from what you've heard?
I think maybe not beyond what I sort of said already. But maybe Dan, I could ask you a question. In terms of what you are doing, is there a lot of genetic engineering in terms of getting better microalgae to do exactly what you want to do?
Yeah, I mean, that's a great question. There's a colleague in the audience here, and we're sort of proposing that question right now, looking at understanding not only sort of what is available from an engineering standpoint, but also getting beyond the sort of idea of model organisms. The algae research community right now uses a very small number of organisms, maybe a dozen or so, to provide a whole host of functionalities, not only building materials, but, you know, fuel, food, all of these other things. Mm-hmm. So understanding what might be possible just within the biodiversity of the 60,000 algae species that are available today, and then from that platform, how do we engineer from that sort of diverse standpoint? So yeah, that's absolutely a sort of new direction that we're sort of actively pursuing.
Yeah, good, great.
Thank you. So now we'll open up for questions from the audience. I don't know how. Thank you.
Thank you. My name is Bill Vanves, and I am the founder and CEO of OneVer Company, which is currently in Scotland, but we're transitioning back home. We're currently now at Harvard Innovation Labs, and we're bringing it back to Boston. So my question goes to Zach, and in the framework that Dan has put, like he defined before, so moving the needle on the green ammonia that you mentioned, or ammonia you mentioned, I'm saying green because we do have a technology that we're working with currently now with MIT, and we are matching the price of the gray ammonia, but we're making it green. How do we do it? We are using intermittent energy from solar and wind and renewable sources, and we're making it continuous with long duration energy storage. And our system matches the, it takes the ammonia down to the price of the gray ammonia currently, as you know, that's where we are. So, and we're thinking there are many applications and new applications with green ammonia, for example, marine propulsion, that we're targeting down the line. So I wanted to ask you if your system also, it's a different ammonia, of course the molecule is NH3, so do you move the needle into a particular point or something? Or if you match the gray ammonia's price, would you transition to nylon and to any other research?
Yeah, that's a great question. And sometimes correct me if I'm wrong, but you're basically sort of asking as you sort of make more green ammonia, what's the best use of it? Kind of the most economical and efficient use of it.
Any other efficiency or any other way to move the needle?
Yeah, and ammonia, right, is it's used for fertilizers, which is kind of its primary use, but it's also used pretty much everywhere else, which I think where things get quite exciting. Is that pretty much, I said all of our carbon comes from fossil fuels. Well, anywhere you see sort of a nitrogen atom, whether it's in like nylon or a pharmaceutical or, an amine, sort of solvents, detergents, that always comes from ammonia. And so turning ammonia into other chemicals like nylon is definitely a good use of ammonia. Right now, there are sort of many steps to get from ammonia to nylon. Even turning ammonia to different forms of fertilizer, right? Urea and nitrates and things like that is a surprisingly energy intensive process. And yet, a large amount of ammonia does go there as well. And that's ignoring sort of all the other specialty products that ammonia is needed for, like, satellite fuels and rocket fuels and things like that along the way there. And so that's kind of where I do spend a lot of time thinking. Happy to chat more, certainly.
Thank you. This is for Daniel. When you were describing the work you're doing, and I was thinking you were working with microalgae that captures carbon, cleans the water, then makes a material that goes through a 3D printer and makes something similar to plywood. I said, this is like a tree, basically a tree, right? Mm-hmm. So how is it more efficient, and what are the difference between all this artificial plywood and planting trees?
Yeah, that's a wonderful question. Yeah, thank you so much. I think trees can be great. Trees are a wonderful form of biomass. Clearly, there's a long history of using them in the built environment. And I think the question comes down to now, how is the production system organized? Right now, we see a lot of monocropping. We see a lot of clear cutting. We see trees that are grown for only 30 to 50 years, where their lifespan can be much, much, much longer. So there's research that has come out, that has been published, that says actually the timber industry is really a net emitter rather than a carbon sink for the environment. So right now, that's the reality. That's not the way it has to be. Obviously, there are more sustainable practices. If a tree falls in the wood and you make a house out of it, that's great. That's a very carbon efficient house when it comes to the embodied carbon. But we also just need to consider the lifespan and the amount of carbon dioxide that the tree could be taking out of the environment instead of sort of being used to make our homes or our buildings. In many cases, the trees could be alive for 500 years more, whereas our buildings might be around for 100, where, to me, that's sort of a medium scale carbon storage. And I'm excited about the idea of, sequestering carbon for 100 years, because I think we just need to be doing things now. I think the tree does a better job of it. So I think that's why we sort of moved away, just given the sort of current production practices.
Thank you.
Thank you for your comments. I appreciate the notion of engineering trade-offs, and certainly as we think about the proposition of the research relative to the costs, I'm thinking within Harvard currently, within SEAS in particular, is there a way to take the research that you're doing in technology to commercialization and scalability and eventually companies? And I ask that in the context of an angel investor. I invest in companies, so I'm looking for technologies that I can invest in. Thank you.
Paul, do you want to take that question?
Yeah, there's various avenues within Seas and within Harvard more broadly for moving companies ideas to translations. There's a Harvard Grid Accelerator, the Salada has an accelerator, there's a whole bunch of mechanisms, and it's actually been quite successful. And actually, I think, Daniel, your effort got some funding through that, is that right?
We've been funded by Salada, but we're not yet in the translational.
Okay, yeah, but the accelerator, but there's various mechanisms that sort of start with sort of get seed funding for getting the first idea a little bit further ahead and then getting sort of into translation aspect. And that's something that's very active and is actually currently growing. It's a growing effort that we have both at Seas, but also sort of at the university at larger scales. And part of the reason for that, as Lena has said, is that we can really leverage the talent here and the fact that Boston really is a green tech hub. And so it's really the right place to really go forward with that. So that's an excellent question.
And I think also maybe I can mention Frank, that in terms of what Harvard is doing now in terms of translation, it also really benefits the students and will benefit the students because they get a chance to sort of be part of that thinking, that whole process. And also our ecosystem and also what we're doing internally at Harvard, give them a chance for internships. And that's something that is like enormously motivating for them in terms of their thinking about the whole problem.
Was there a question right next to you? Oh, no, okay. There was also a hand somewhere over there earlier in the back. No, perhaps not. Then, okay, sorry. I'm hallucinating.
Hi, hello, good afternoon. I'm Glenn from Manila, Philippines. What is the present carbon footprint of Harvard University? Because we know that you have lots of initiatives on how you're going to reduce your GHGs or your carbon footprint. So my question is, what is the present carbon footprint of Harvard University? Thank you very much. Because if we fail to do that, it will be very hard for us to create a net zero emission roadmap. All right, how we're going to reduce it for the next 5 years or 10 years. So that's my question. Thank you.
I don't know the carbon footprint of Harvard, I have to admit. I don't know if there's somebody else in the audience who can speak to that or has an idea. So I'm sorry.
Actually, I have that number on my computer, but my computer's turned off. So that's off the top of my head, so I don't want to speculate on that. What I can say is the Office for Sustainability here at Harvard has been working for a long time, like 13, 14 years, on decarbonizing. They've made actually tremendous progress on buildings. Our footprint in buildings has gone, energy consumption in buildings over the last 12, 13 years has gone down by 30%, despite the fact that we've increased our footprint by about 30%. So really substantial per foot reduction. We're electrifying our transportation fleet. So if you look out in Harvard Square, you'll see electric buses going around, and we're doing that as they roll over. The next big step, which is a really big challenge, and I'll just be frank about this, is thinking about the heating and cooling in this building and the heating and cooling in all of our buildings. So the cooling is electric, but it's the heating that is really the big next stage. Oh, from all sources of GHGs. Our overwhelming footprint comes from carbon emissions. Right now, at this point, I'm just thinking about scope 1, scope 2. So we have some scope 2 that we're purchasing, but we also do our scope 1. And for example, we have 2 units that are running steam heating systems, low temperature non-steam and a high temperature steam on the other side and the question is, how do we decarbonize those? And those studies are in process. So that's a commitment that we're making, and we're doing it. But because they're system-wide steam heating systems, and on the other side of the river, a low temperature, 140-degree system, you want to sort of do that systematically and think about what the right way is that's going to interconnect everything. So that's where we are. Well, I mean, the big remaining, so we want to decarbonize our electrical purchases, and we're actually in the process of doing that, and that's now, given wind and solar prices and PPAs and so forth, that's actually the easy part. The hard part is the...
Yeah.
Great.
Yeah.
And they'll be able to tell you that more.
Great.
Yeah.
There's a whole section on carbon greenhouse gas emissions.
Yeah.
Thank you.
University-wide scope 1, scope 2 greenhouse gas emissions. It only has scope 1 and scope 2.
Yeah, scope 1 and scope 2.
Right now,
All right.
I think we all recognize how hard scope 3 is, given that right now, even in the US, we don't require scope 3 reporting for any company whatsoever, although we're starting to do that. So, and I think you would want to look at the greenhouse gas protocols for how to measure scope 1 and 3.
Thank you. We'll take what we're running out of time. So, okay, I'll see two more questions. First in the back, yes, there, and then one over here. on the left.
I'm Greg Beyer. I live in the area. Just on the follow-on to that, what are your thoughts, or how is the university preparing and using its technology base for the water rising? I live at 4 feet above sea level in Arlington, and I just keep wondering as I drive by, water's going to go up eventually. You know, there's this enormous built environment, this real jewel of an institution, and I just wonder. Same for MIT. I've been dying to ask the MIT guys, what's the plan? Or, you know, how are you guys thinking about, keeping the place high and dry?
That also may be more. I'm not aware of this. I think your point is, will the river houses turn into a river? But I don't know whether Jim can make a short comment on that. That's a little unfair of me, but I don't really have an answer for that.
I guess I would just say
That's a really huge question. So thinking about that sort of adaptation, and so that any adaptation, it's not like Harvard's going to build a moat around Harvard and let MIC sink and let Back Bay sink. So this is, I mean, some of us might think, but whatever. So this is really a citywide, region-wide challenge, thinking about sea level rise, which is not going to be in the next couple of decades, but for sure, if you look at the NOAA maps, this is something we need to be thinking about at an end of a century timescale. So I take the point. I take the point, and that is a regional planning, Massachusetts planning problem.
One more question over here on the left there. Thank you.
Thank you. My question is for Gage directly. So like you said, the load growth in data center are a huge problem. We're going to see 15% load growth just because of AI. Hasn't happened in a decade. And question is, how do you think it's more of a hardware issue or a software issue? Like, can we improve efficient algorithm at the first place? For hardware, I know you're focusing on hardware, I believe. Are you focusing on new materials as well that can be more efficient in computing?
Yeah, that's a great question. As a hardware designer, I'm going to say it's hardware. But of course, it's both. And this is, I had sort of mentioned before, this project that project that we've been working on with National Science Foundation that just funded. I mean, it's exciting that these kind of problems for computing is like being recognized as very important problems. So our team, like from Harvard, includes me on the kind of like low level. I mean, the answer is everything, but I work on the kind of like low level materials and devices. Like, what are the most like efficient materials to make transistors moving forward? The sort of physical design of the chip. We work with Guyan Wee, also in electrical engineering, who's on the kind of circuit side. It's David Brooks, like sort of going up the stack on the sort of computer architecture and software side. Minlan Yu is even also in computer science on the like computer networking side. There's people from our team at other universities, at like Penn, for example, is a partner university that we've been teaming with. There's a guy there, Benjamin Lee, who's a student of David Brooks's, that's also kind of working on the like the software side and like algorithms, exactly like you said. There's people from like Caltech and Columbia, Emma Strubel, people from Yale, Yuan Yao, looking at this kind of like policy side. So I think this is really exciting. This is recognized as kind of like a global problem that like everybody sort of has their hand in and realizes that it's like super important. we don't totally know how to figure it out yet, which I think, obviously means there's a lot of room for innovation. So yeah, I mean, everybody has a hand in this.
All right, thank you very much. Let's thank our wonderful panel again.